Okay, now let's talk about NP hard and NP complete problem. It's a special category of NP problems. We have categorized into two, NP hard and NP complete. So let's see what they are. So R is a polynomial time reducible to Q. So if R is any problem which can be reduced to Q, we are denoting this as R, Q in polynomial time. So the notation used for reducing the problem from one form to another. So R is one form of problem which can be reduced to Q. In a polynomial time, we can write this as in this way. A definition of NP hard and NP complete can be this. If all the problems are, that is NP, are polynomial time reducible to Q, then Q is NP hard. So if we consider a set of problem, let's say this is a NP set of problems. So if we say this all the problems, we are calling it as a R. If all the problems are, that is actually belongs to NP, are polynomial time reducible to Q, then Q is NP hard. So if we are able to represent all these problems to one problem Q, then this Q set is said to be a NP hard. So if all these problems are able to be represented by a single problem Q, then Q is said to be NP hard, or you can say this is the hardest problem to solve. We say the Q is NP complete if Q is NP hard and Q belongs to NP. So the meaning of here is, if this Q problem is somewhere out of this set NP, then it's said to be hard. But if you consider a scenario where this is a problem set NP, and these are, let's say, these are representing the problems which are non-deterministic polynomial time problems, and if we are able to represent all these problems to one problem which is still a set of NP, then this is said to be NP complete. So the difference of NP hard and NP complete is, if the problem itself which is representing is a part of this NP set, then it is an NP complete. But if this is represented as the outside problem, then it is said to be a NP hard problem. So if R is reducible to Q in a polynomial time, and R is NP hard, then Q is also NP hard. This is the assumption that we have to take. Now, why we study this NP complete problems? What is the purpose of understanding the concept of NPC? So the most important reason is, whenever you come across any new problem, and if you want to develop a solution, you can stop from spending time and energy to develop a fast polynomial time algorithm to solve it. Now, if you are aware about the NP complete problems, if you are aware about the characteristics of NP complete, so if you find a new problem uh, uh, which is not immediately to solve, and you're looking for a solution, it's better to compare the characteristics. You have to check the characteristics. You need to check that is it possible to convert a new problem into a already existing NPC problem. If it is possible, then that means the new problem is also the NP complete problem, and you cannot determine its deterministic polynomial running time. Now, how to prove a problem is an NPC problem? So if a new problem alpha is coming across to you and you are looking to find a solution for it, so uh, because the problem is very new and you are interested to find a solution. Now this problem may be hard problem, means maybe the solution for this problem does not exist in a polynomial time. You cannot write the deterministic algorithm for it. So it's always better to check that what is the nature of the problem. So we will try to reduce this problem into some known NPC problem. If we are able to reduce into the known NPC problem, now this process are actually slides easier than to find the exact solution of this problem. If we are able to reduce this problem into the known existing NPC problem, then it determines that this is also a NP complete problem. That means this is also a hard problem, and there is no known existing deterministic algorithm exist for this kind of problem. Now, how to prove that this is NPC problem? So there are many known hard problems are existing like 0-1 knapsack problem, traveling salesman problem, sum of subset problem, graph clearing problem, Hamiltonian cycle problem, satisfiability problem. So satisfiability problem is actually the fundamental problem we have, we normally take to represent for reduction. So whenever a new problem comes in picture, we try to reduce to the satisfiability problem. So we have to choose one NPC problem B, and then we have to develop a polynomial time algorithm that can reduce the problem A, the new problem, to B. So we need to write a reduction algorithm. Now already we have discussed, to write a reduction algorithm, we must satisfy the two conditions. So if you are able to write the reduction algorithm in polynomial time, writing a reduction algorithm in a polynomial time is a quite easier task than finding a overall solution for the new problem. So if you are able to write a reduction algorithm in polynomial time, that means you are able to identify that what is the nature of the new problem. Now here you can see the statement, if a problem A can be solved in polynomial time and it can also be reduced to B in a polynomial time, but B is solved in a non-polynomial time or it is non-deterministic, then A cannot be solved in a polynomial time. So by using this kind of assumptions, we simply make an approach that whenever a new problem is given to us, instead of finding the actual solution for it, because we don't have any input for this to proceed for the solution, what is the easier task is we try to make a reduction, we try to develop a reduction algorithm that can convert to B. So if it is possible to convert to B, that means the nature of this problem is also NPC. This is also belonging to the hard problem category. If it is not convertible, that means this problem is a problem which can be solved in a polynomial time. So what if a NPC problem need to be solved? If you forcibly willing to solve the NPC problem, then what is required? Definitely, we have discussed that these problems have a non-deterministic algorithm. When I say non-deterministic, means all the steps of the algorithms are not very clear. The steps are making some guesses, and when you make a guess in your algorithm, when your steps are not very clear, then it is not actually easy to work on existing machines. So one solution is, already we have seen that these problems are having an exponential learning time. They will take a huge time to give the solution. So one solution is you may buy a very expensive machine, and even with the expensive machine, we have already calculated. You can go with the calculations of some hard problems. You may realize that solving these problems may require maybe 1,000 years or more. So this is one of the solution, that you can buy an expensive machine and can wait for a longer time to get the exact solution. The other problem, the other way of getting the solution of these kind of problem is, we go to approximation algorithm. So approximation algorithms are basically give a near optimal solution, not exact solution, because so far we don't have a exact solution existing for these problems, but we can go for the near optimal solution. So we can say that approximation is basically when we don't have the deterministic solution to the problem, and we go for the approximate solution. So this is what we can do to solve the NPC problem. So far we have discussed what is NP hard, what is NP complete, and what is P and NP problems. So let us conclude that we have simple problems. Simple problems are the problems which can be solved in a polynomial time and can be verified in a polynomial time. Hard problems are the problems which cannot be solved in polynomial time but can be verified in a polynomial time. So whenever a new problem comes across and we are looking for a solution, we always go for the reducibility. So reducibility is a concept where we are trying to convert one problem into another problem in a polynomial time. Then we have seen that this is a set representing NP, and then we have, if we represent all these problems uh, to one set, then this becomes NP hard. And if all these problem can be represented to one problem which is still a part of this NP, that is called NPC. And if we combine these two, then we can get this kind of figure, that this is your NP problem and this is your NP hard and this is your NP complete. So we are able to represent all these problems into one, which is also the part of NP problems. And also there is one more assumption, though we have many argument on this, but there is one notation that has also been popular. You may come across. We write P equals to NP equals to NPC. The meaning of this is that though we have identified what are the NP complete problems, we have identified what are the hard problems, we have categorized a number of problems as NPC, we have identified the characteristics, but there is an assumption that if somehow we are able to solve any of the one NP complete problem. Now NP complete problems are actually representing the hardest problems of NP. Okay, so if we are able to solve any of the problem of NPC, then we can use the same strategy to solve NP problems. And if we solve all the NP problems, then actually all the problems can be said to be a polynomial time algorithms. So this is one notation that is actually used, but the meaning of this is that somehow we are able to get in future the solution for one NPC problem, then the same strategy can be used to solve all other problems, because we have already discussed that most of the problems are actually represented in the form of reduction. So when we talk about the different problems like table assessment, 8 queens, sum of subset, graph coloring, Hamiltonian cycle, all these problems are interchangeably reduced in one form to another, and has been proven that these are NPC problems. So this is all about the basic introduction about the P and NP problems, and this area is something which is always having a lot of scope for research. So if you are interested in the research, you can just go through to the new emerging problems. We have discussed the basics of different categories of problem and how they are being categorized. And this is an open research area. Now you have got the foundation of P and NP problems. You are in a position to explore more into this area. Thank you very much. This is all for this lecture.